The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. My name is Catherine. I'll be your webinar facilitator today. I'd like to welcome you and thank you for joining us for the VRV Life Balance Point Application webinar. As a reminder, all lines are currently on mute to prevent background noise. If you have questions during the presentation, go ahead and type them into your chat box. We'll be happy to answer at the end of the webinar. This morning, it's my pleasure to welcome Sean Turner, Applications Engineer. Sean, you may now begin the webinar.
Alrighty, thank you, Catherine. So today the core topic that we're going to be discussing is balance point application. So the concept of balance point and how it relates to VRV Life, how it relates to sizing and selecting and designing VRV Life systems. Now, before we get into that, I just want to introduce the applications engineering team. So introduce them and kind of discuss how we're a resource to those of you who are listening in. So first off, who are we? We're led up by Robert Powell. He's the manager of the applications engineering team. We work out of Houston at the DTTP, the new facility here. And then myself, once again, my name is Sean Turner. I'm an applications engineer. Been with Daikin for about 2 years now. Prior to Daikin, I was working on the hydronic side, also as an applications engineer. So I have a number of different focus areas that I'm currently focusing on. Obviously, one of those is VRV Life. So I kind of champion VRV Life training and questions and that sort of stuff. So we have a few other members of the team as well here in Houston. Chris So, great source for outside air questions. And then we also have Nick Trapani, and he's real good with competitor comparison questions. So what exactly do we do? So overall, we're a resource to all of North America on any Daikin products. So we support internal Daikin sales managers as well as distributors, manufacturers, reps, contractors, that sort of stuff. And there's a number of different channels that we use to get information out as far as how to design new systems, how to apply the product, how to optimize selection, that sort of stuff. So some of those channels being obviously webinars like we're doing today. We also have a number of technical presentations and lunch and learns and design workshops, which I'll talk about here in a second, but those we actually go out and deliver in the field. We're very familiar with codes and standards that are applicable to our products and involved in networking events and seminars and that sort of stuff. Now, we also create and maintain a portfolio of applications and reference guides, and one of those being a VRV Life reference guide. So that reference guide is going to have a lot of key information in it. One of the topics being balance point, but there's a whole number of things in there like piping lengths and details on the receiver tank that you may need to use in a VRV Life system, as well as just overall general application guidelines and rules and that sort of stuff, and a lot easier source than trying to sift through maybe an installation manual or engineering manual. So that's available up on Daikin City in digital form. You can also order it through the literature portal, and it comes in a little pocket-sized print. So it's about the size of your hand. You would have to have kind of big pockets to actually fit in your pocket, but it's a nice, easy thing to throw in your bag and have available and just easily access quick key information for laying out these systems. Now, I mentioned design workshops, so we have a number of these available. The one that I'm going to talk about here is the VRV Life Design Workshop. So that focuses on bringing our distributors and contractors up to speed, or anyone who's involved in the design process of VRV Life systems up to speed in a very quick manner. So it's kind of broken down into four main parts. The first part that we'll go through is actual presentation based. So we'll go through a lot of the key benefits and features and that sort of stuff. But then the real main focus is to drill down into the finer details of how to apply those benefits, how to apply those features, how to size the systems, how to select the systems, and then also how these systems just fundamentally work. And then there's also a design portion, and a real big benefit of these courses is actually going through and learning the software. So you may be familiar with it a little bit already, but actually having somebody who's an expert in it by your side as you're maybe as you're first learning it or getting more familiar with it is really beneficial. We get a lot of positive feedback in that nature from people who go through the course. And then obviously, part of the course is we give blank floor plans, and the attendees will actually put together a design themselves. So all the information that attendee would need to put together that design is presented in that beginning portion of the class. And then we'll go through the solutions and summaries and that sort of stuff at the end of the day. So once again, those are available to anyone who's involved in the design process of VRV Life Systems. And if that's something that you would be interested in, I would recommend reaching out to your local Daikin sales manager, TSM or ASM, and they can coordinate setting that up and reach out to us being applications engineering. All right, so now that we got the introduction of the team out of the way, I want to get to the core concept. So what is balance point? Now, before we do that, I want to start pretty basic and kind of go over what fundamentally a VRV Life System is. So in its simplest sense, it's an air source heat pump. So what that means is an air source heat pump just simply moves, so we're going to be talking about heating today. So in heating, an air source heat pump is going to take air, or take heat that's already available in the air outside and just simply move that heat to the inside. So we're not creating the heat by burning fuel or anything like that. We're just simply moving that heat. It takes about 1 unit of electricity to move that heat from outside into inside, and we get 4 units of heat out of that on average. So as you can see, it's a highly efficient means to condition a space. There is some caveat. Air source heat pumps performance is impacted by the ambient conditions, so by the temperature of the air outside. And that goes contrary to some of the traditional residential solutions like we're all familiar with, gas furnace and electric heat. We don't see that impact, so it's not something we necessarily had to consider if that's what the solution that we're familiar with. Now, how significant is that, particularly here in North America? So historically, air source heat pumps have realized most of their market growth in temperate climates outside of the U.S. North America tends to be a little colder. You can see just from that map there, on average, that from the larger cities, the average design day conditions average together for the states there, you can see we're below 32 degrees Fahrenheit design day temperatures for heating for a majority of the U.S. And then in addition to that, residential applications tend to be heating dominant. So that doesn't always mean you're heating more days out of the year than you're cooling, but it does mean that your heating load is larger than your cooling load. So now we're designing our systems for heating rather than cooling. So a lot of those traditional rules of thumb of maybe a BTU per square foot based off of an AC system, a system that only cooled, are no longer going to apply. And then we're also, like I said, impacted by the ambient temperature. So what that means is we lose capacity as it gets colder out, and that's exactly when we need the capacity the most. So we lose capacity as the load increases. And then we do have limits as far as how cold we can heat down to. So on a VRV Life System, that's going to be -4. So what do we do for some of those areas on that map we see that are below -4 degrees outside? Now, before we discuss that solution, I just want to kind of provide a little more information for those of you who are interested in why we lose capacity as it gets colder outside. So I promise this is the only time you'll see a pressure enthalpy chart throughout the presentation. So in the bottom left corner, that's a pressure enthalpy chart, and just in the simplest sense, a pressure enthalpy chart has a horizontal line on the top. That's the high side pressure of the system, or the temperature that we're releasing heat inside. And then we have that bottom horizontal line that represents the temperature that we're absorbing heat from the outside. So the temperature that we're releasing heat inside, that stays constant. So that's a target temperature. We're trying to keep that constant. What does vary is the temperature that we're absorbing heat from the outside. So obviously we want to be colder than the air outside so we can absorb heat from it. So as that temperature decreases, we're continually dropping that temperature, that evaporation temperature, so we can continue to absorb heat out of it. And there's a few things that happen when we do that. The most significant factor is the density of the refrigerant is decreasing. So it's reducing the volumetric efficiency of our compressor, less mass actually flowing through it. So that's going to contribute to the capacity loss a good deal. And then you can also see in the bottom left corner of that red shape on the pressure enthalpy chart, the farther that corner gets away from that dome line, that dark dome line, represents the more vapor that's present in the evaporator. So vapor's already evaporated, it can't absorb any more latent heat, so just getting a free ride. So ideally we want to just have pure liquid in the evaporator so we can evaporate it all and absorb all that latent heat, but that's not the case. And it gets worse the lower we're dropping that temperature. So it's just increasing the pressure drop in the evaporator and getting a free ride. And then also the distance between these two horizontal lines. The more that increases, the more energy it takes. The more work the compressor has to do to bring that pressure up from the low ambient conditions up to the constant temperature that we like to see on the indoor side. And this all results in what you see on the right-hand side there, capacity curve that starts to drop off as it gets colder outside. So really, it's not going to be too significant until around 20 degrees outside, and it's going to depend on a lot of factors. So this just represents a fixed set of conditions, just giving you an idea of what that looks like. But the general sense is around 20 degrees, you see a more significant drop in the capacity. And you do see a downward hump kind of between 20 and 40 degrees. And that's when defrost is a factor, when there's enough moisture in the air where frost is building up on our coil, and we have to go through this defrost cycle to melt that off, so we're not impacting our ability to exchange heat on that outdoor unit. So we've kind of painted a picture of using air source heat pumps being challenging in the North American market. So how do we get around those challenges? Fortunately enough, we have VRV Life, which was designed specifically for the North American market with those challenges in mind. So one of the best things about VRV Life is we're able to integrate a gas furnace and a coil. So that traditional solution that most people in the residential industry are familiar with, we can easily integrate that into a VRV Life system, have that operate during those peak days out of the year, so maybe a handful of days out of the year, and then we can use that highly efficient means to condition the home for the rest of the heating season. So it's a truly optimized system. There's also some additional ability to integrate electric heat. Some of the indoor units available to the systems have factory options for that, and we also have some control options as far as staging some third-party electric coils on some of the other indoor units. So that's ultimately going to allow us to extend the reach of an air source heat pump solution into some of those colder climates in North America. So that's how we're going to be able to have a VRV Life solution in a climate that has a -4 degree or below design day temperature. So how do we size the system now that we have these two sources coming together? How do we know when to switch over? So traditionally what you do is if you just had an air source heat pump system, you'd select it based off of that design day temperature. So it would always have to meet that design day temperature, so it's going to be large. It's going to be larger than it would if you were sizing based off of, say, a balance point. So that introduces this balance point curve that I want to talk about. So on the vertical side, we have the heating load. On the horizontal, we have the outdoor temperature. And what you see here is that capacity curve. It's a simplified curve from what I showed earlier when we were talking about why these systems lose capacity. And then we have our heating load. So as it gets colder outside, our heating load is increasing, and our VRV system's capacity is decreasing. Eventually, those lines will decrease. Now you can see if we needed a system to meet that design day load, we'd have to increase the size of our system to meet that, or you could use some sort of supplemental source to meet that small portion of the heating load or heating requirement, and have the VRV system meet that the bulk of the load. Now there's really a few different types of auxiliary heat that can be used for this balance point concept. So the first one being alternative heat, and what that essentially means is you're switching over from air source heat pump heating to an auxiliary source. So, for example, gas furnace. So you're switching entirely over. You're not operating those both at the same time. So in this case, we would switch from the CXTQ, that A coil, block that out, and run the gas furnace. The other option would be a supplemental heat source. So that's working in tandem with the heat pump. So a good example of that would be the multi-position air handling unit, the FXTQ. So we have the ability to have that FXTQ continue to provide heat pump heating, and a supplemental source only come on and work in tandem with that unit when it's struggling to meet that set point. So let's take a look at an actual example. So the first example we're going to look at is that alternative type of auxiliary heat source. And we have a single-story residential floor plan here. We have a gas furnace and an A coil serving the main area of the home. And then the master bedroom is broken off on its own zone. So this master bedroom, that FXSQ, that medium static ducted unit in that master bedroom, is going to have to be sized based off the peak heating load because it doesn't have a secondary source available to it versus the CXTQ, the A coil, that does. So we only need to size that based off of cooling because we're always going to have the option of switching over to that gas furnace. So what that looks like on that balance point curve that we were just looking at, so we have our total heating line. So that's a sum of the heating load within the main area and then the heating load within the master bedroom. So this total heating load line, once that intersects the capacity of the VRV system, we have to lock out that A coil and shut that off so that the capacity of the system is available to the master bedroom because it has no other source. So we can take the A coil, shut that off, and run the gas furnace and make that capacity available to the bedroom because there is no other option for that. So you sort of have a supplemental type of scenario going on here, or it's kind of a mix between the two things we were just talking about. We're still running the heat pump for that master bedroom, but we're running the gas furnace for the main area there. Now, you may have noticed I've thrown indoor unit in the garage and didn't really mention anything as far as sizing of that within the system, and that's just one benefit we have within these systems. We can throw these secondary sources where heating and cooling isn't critical and it doesn't really impact the sizing of the system, provided you have the additional connection capacity or connection index available to add that into the system. You don't necessarily have to size your outdoor unit to meet the load within that space, but we can still have the option of tempering that air for those non-critical days. So we've introduced this concept of balance point. How do we determine what that balance point is? Fortunately, we have WebExpress, the selection software that's going to do it for us with some information that we provide to it. So obviously it's going to know what the capacity of the VRV systems are. That's already built into the selection tool. And once we enter in what the design day temperature is and what that heating load is, it's going to determine a heating load curve. So it assumes by default at 65 degrees outside that there's no heating load. So that's a pretty standard ASHRAE condition, 65 degrees, no heating load. And then you're assigning that heating load as well as when that heating load is occurring outside. And it's just going to draw a linear line between those 2 points and tell you where they intersect. And you'll see as the system gets larger, that intersection point shifts to the left. So you're switching over at a later point in time. And that makes sense, right? Because you have more capacity on that system. You're not going to run out of heating capacity until it gets a little bit colder outside. And then if you're familiar with WebExpress, the conditions for the gas furnace, those are going to be present on the selection of the A coil, and this will also be present on the outdoor unit properties pane. So it's going to be labeled as a recommended balance point, and in this case you see with a 5-ton unit it's 15. So let's look at some numbers. That same example, just throw some numbers to that example. So we have a heating design day temperature of -3 degrees outside, 45 MVH load for that main common area, that gas furnace and A coil, and then we have a 15 MVH load for that master bedroom. So the total load line is that red line there. It's a sum of those two, and that occurs at -3 degrees outside. And that's going to intersect a 4-ton capacity curve at around 16 degrees. So the balance point is provided in increments of 5. So it's falling on 16 degrees, so it's going to round that up to 20 degrees. And it's obviously always going to round up. You never want to actually round down. So in this case, 20 degrees is when you would switch over based off of that 60 MDH load occurring at -3 degrees outside. Here's another example, except now we're looking at something that's outside of the design day temperatures, outside of our operational envelope on the heat pump. So it's -10 degrees. VRV systems heat pump heating is supported down to -4 degrees. Doesn't mean it's going to lock itself out at that, but the supported operational envelope is -4. So in this case, we have a heating load of 50 downstairs, heating load of 45 upstairs. The total low line is going to be 95, and that's occurring at -10 degrees outside. And we're going to get a balance point temperature of 25 degrees in this case. So you see 21 degrees, again, we rounded up, and it's 25 at the point that we would switch over. Now it's important to, in this case, assign the correct design day temperature for your gas furnace, because this is the heating load is being pulled from the gas furnace, and that's how it's drawing this heating load line. So if we were to put -3 in here for that, it's going to change the slope of this line and then change that balance point. So you want to make sure you have your heating load and your temperature at which that heating load occurs matches up within the selection tool. So now we found out what balance point is. We found out that WebExpress calculates for us. We looked at a few examples, and then now we're going to look at how to actually apply it to the product. So there's a field setting on the outdoor unit. By default, it's 15 degrees. So if you do nothing, that A coil is going to lock itself out at 15 degrees and bring on the gas furnace. But it's configurable in 5-degree increments, as low as -5, as high as 50. And you can also force gas furnace only, or you can force no gas furnace at all. And that's, again, a field setting on the outdoor unit. It's 214, and you can find the same information available in the installation manual or the service manual. Now we're telling the gas furnace when to come on. There's also a setting associated with when the gas furnace is going to shut off. So this setting, the main objective of it is to avoid scenarios where the gas furnace is coming on and off, and cycling. So by default, if it were to come on at 15 degrees, it's not going to shut off until 25 degrees outside. So that can be set as low as 5 and as high as 15. And again, that's just to avoid having the gas furnace coming on at 15 degrees and then shutting off because it bumped up to 16 degrees. You want to avoid any sort of short cycling. So now we're going to look at another example, but this time supplemental heat. So the FXTQ, like I mentioned earlier, is a good example of that supplemental heat with an electric heating source. So we're kind of looking at that same example we looked at earlier with the gas furnace and A coil, except we've switched the gas furnace and A coil with a FXTQ with some electric heat. So very similar scenario. You'd size this unit based off of peak designed at heating, and then this unit you could size based off of cooling with the keeping in mind that you have electric heat as backup, provided you were in a climate and application that needed that backup heat. So one great thing about the FXTQ and the logic built into it, and also the control options for our other indoor units, is there is really no concept of calculating a balance point. It's a supplemental heat source. They're going to work in tandem, and there's the logic there to bring on that electric heat as it's going to see at the unit struggling to meet set point, and it will come on automatically and help that unit meet set point. So there's configurable on values. So say you're 3 degrees away from set point, you can have it come on automatically. And then there's some electric heat options that are multiple stages. Some of the larger electric heat options go as high as 2 stages. So there's a second stage as well, which is not configurable. There is this S value So that's just an automatic setting that optimizes the on and off temperatures based off of trending of set point versus room temperature and your room temperature over time. Just optimizes those values automatically for you. Now looking at that same example, but the only thing I've changed here is the climate. So it's a more temperate climate, heating designed a temperature of 28 degrees. So maybe that's northern Texas could have a design day temperature of 28 degrees. So total load is 65. So this is an all heat pump solution. In this scenario, based off 28 degrees, our outdoor unit heating capacity is going to be 53 MVH, and our heating load is 65. So we're a little bit short. It equates to around 11,000 BTUs an hour short, which is around 3.3 kilowatts. So it's pretty small. So in this scenario, our only option really is to put a 3 kilowatt electric coil, because that's the smallest we have in each one of those units. But if it was larger and you needed to actually size electric heating, you could proportion that needed electric heat per the size of the indoor unit. We see that same balance point curve, but again, remember, we don't really need to calculate a balance point. This is going to come on automatically and help the unit when it sees it starting to struggle to meet that set point. But it can be useful to do something like this to get an idea of the gap between the capacity and the load. Or you could just take these values from WebExpress. You know what your load is, you know what your heating capacity is, and the difference between those is going to be what you need to size your electric heat for. So one great benefit of having this auxiliary heat source too is we can run it during some of the special operation modes like oil return and defrost, and that's available on both the A coil, the CXTQ, and the multi-position air handling unit, the FXTQ. So these are the field settings associated with that. Essentially, you can set once the gas furnace comes on to help out during oil return and defrost, it's going to run for either 15 minutes, 30 minutes, or 45 minutes before it shuts off. And then on the FXTQ, you can set it up. Basically, these are the two settings associated with running it in that special operation mode, but you can have it provided or be used as a supplemental source in 8 or not used and only used in defrost and oil return. So up until now, we've just been talking about balance point in respect to capacity. So what physically can the system do before it runs out of capacity and we have to switch over to a supplemental source or switch part of the system over to a supplemental source. So we have the capacity available to other zones who don't have a supplemental source. But there's really a number of factors that come into play as far as balance point. So capacity is just one of them. The other most significant one would be operating costs. So what does it make sense from a cost of fuel standpoint to run? Does it make more sense to run electricity or natural gas, which is going to cost me more? So that's going to be dependent on a lot of things, primarily your local fuel costs. So you see we have two different efficiency furnaces in the gray, and then we have the RXTQ 60, or that should say RXSQ, that's an error there. And then we're plotting that in dollars per million BTU. So how much energy, or how much money does it cost me per million BTUs? And you see the gas furnace is staying constant. It's not affected by the ambient temperature, but as it gets colder outside, it starts to cost you more per unit of energy to run that heat pump. And you can, very similar to what we did with the capacity, you can plot those and get an idea of what that intersection point is and when it makes sense to run one versus the other. So in California, electricity tends to be very expensive. So you see a switchover point that is on the higher end. So we're looking at close to a 50-degree switchover point in that case. That's based off of the average electricity rate in California. But in Louisiana, where electricity is much cheaper, it makes sense to run that heat pump as long as you possibly can. There's other factors to consider as well. Not all areas have natural gas available. So if you're in a location that's maybe running off of propane tends to be very expensive, or more expensive than, say, electricity per unit energy. So you'd see something similar to what we're seeing here with Louisiana, where it would make more sense to run that heat pump as much as you possibly could. So overall, we saw that in the North American climate, it's not necessarily a temperate climate. It tends to be more towards the colder end of things as far as design day heating temperatures go. So it's been kind of a barrier to more rapid air source heat pump adoption. More of the heat pump adoption has been in the southern parts of North America. And another thing that's not really working in our favor is the residential applications. The heating load tends to be larger than the cooling load. And again, that doesn't mean that you're necessarily heating more days out of the year than you're cooling. It just means that the design day temperature, or I'm sorry, the design day heating load is larger than the design day cooling load. You'll see in most cases the difference between not having a load and your design day temperature for heating is much greater than the difference between that for cooling. So this introduces the concept of balance point. So we talked about what balance point is. We talked about how WebExpress calculates it for us. We looked at a few examples. We looked at how to apply it to the outdoor unit. It's a field setting on the outdoor unit. And then we also looked at different aspects of it. So capacity being the main one, what physically can the system do? But there's other things we want to consider as well. So what makes sense from an operating cost perspective? And considering that piece, the operating cost perspective is really something that's going to benefit your customer. That's really what they care about, right? And VRV Life systems, they're optimized for this North American climate. They're designed specifically for North America with all these factors in mind. And that's why we're very flexible as far as our ability to integrate auxiliary heat sources. So we have that gas furnace and A-coil capability, that solution that's very familiar with the industry. We can easily integrate that into the system. And then we also have other options, smaller electric heat options, so we can integrate those as factory options on some of the units. And then we also have some control options to stage and interlock other third-party electric coils with our systems. So with that, I'm gonna open it up for questions.
Okay, great. Thank you so much. So if you have questions, go ahead and use your chat box. We'll be more than happy to answer your questions. I did want to mention you will receive a follow-up email a little bit later today with a link to the webinar recording. So if you'd like to refer back to it or share it with someone who might be interested, you'll have that in your email. It's the automated email from GoToWebinar that says, thanks for attending if you're here live, and clicked that web link. If you are listening to the audio portion only, or maybe in a conference room with a group of people and only one person clicked that link, you might get the one that said, we're sorry we missed you. There are a few cases you might get that, but also in the body of that email will still be the link to the recording. So a few questions here. Oh, and of course there's a post-webinar survey, so feel free to let us know how we did. A few questions here. The balance point calculation makes sense based on heating load requirement. Is there a calculation that WebExpress can do to optimize the switchover point from HP to furnace for cost of operation?
Not currently. That's a good question. Not currently built into WebExpress. It is a calculation that if you reach out to the application engineering team, we can help you with. We do have some tools, some Excel tools that can help you do that. But unfortunately, right now, it's not something that's built into WebExpress. Okay.
Which generation of FXTQ will be supplemented? I'm sorry, let me try that again. Which generation of FXTQ will allow supplemental electric heat?
So I know for sure that the T series allows that. I'm not exactly sure off the top of my head for the older series of the FXTQ. That's something I'll have to get back to you on.
Okay. Just some follow-ups from David regarding the cost of operation. I'd like to be able to put in the cost of electricity and natural gas, maybe an Excel sheet is a suggestion. And also, what email should we use for the cost of operation inquiry?
Yeah, so that's exactly what we have. We have an Excel sheet put together. You can just you'll have to change a few things, obviously, the cost of fuel in your specific area. And the email you can reach out to is applications.engineering@daikincomfort.com. So applications.engineering@daikincomfort.com.
Perfect. Thank you so much. This winter, we received multiple calls about heat ice buildup on the condenser and large ice buildup on the drain pan. Is there a plan for including a base pan heater in the future?
So that is another thing I'll have to follow up on. I know currently we don't have an option, but yeah, I would just be guessing right now if I were to speculate on that.
Okay, so Jeremy, we will look into that, and thanks for the suggestion. Can electric heat be locked out via controller if we want it installed just as a potential backup?
Yes, so there's a field setting. So the field setting was actually on one of those slides. That slide where we talked about using the supplemental heat in that special operation mode for the FXTQ. There is a setting on in that table where you can restrict it from operating in a supplemental manner.
Okay. When the outdoor ambient temperature reaches -4 with the VRV Life outdoor heat pump and the FXTQ indoor air handlers with electric heat, does the heat pump shut off and just supplement electrical heating is running to satisfy the space temperature?
So there's nothing that's a hard cutoff, so it's not going to force the system off. Just beyond -4, we can't guarantee any sort of performance. So that we've supported the full operational envelope, all sort of conditions you could possibly have down to -4. Beyond -4, we don't have performance data. We don't know when any sort of safeties might kick in and start limiting the operation of the compressor, say, because of low pressure protection or anything like that. So we'll continue to operate down to what point and at what capacity, I couldn't tell you.
Okay. Will the furnace run into frost even if the outdoor temperature is above the switchover temperature set by the mode 2T4, I think is what it says. When running during defrost, is the furnace controlled based on room temperature, or does it run low-high heat for the duration of the defrost time? Oh, 2 through 14. Sorry.
Not sure if I understand the question. Maybe they can reach out to the applications engineering email. It sounds like a detailed question that I would have to look into.
Roby, if you can reach out, that would be great. And at this point, I think that's all that we have. I think we've answered everything here that we can. There are a couple of things we'll get offline on. And Richard, I'm not quite sure about your comment. My Boston Mass company has installed 100, so thank you for that. We like that you've installed a lot. Can the gas furnace design temp drop to -36 Fahrenheit on WebExpress? This is the design temp in Northern Canada.
That's a good point. There's nothing yet physically preventing a gas furnace from operating that low. And yeah, we'll look into that and see if we can have that.
Okay, perfect. Well, great. So thank you so much. Lots of great questions and comments. And certainly if you think of anything else, you can reach out to the applications team. You can always tuck any questions in on your post-webinar survey. I'll be forwarding all your questions and comments and feedback over to Sean a little bit later today. And Sean, I wondered if there's anything you'd like to say in closing today.
Just thank you everyone for coming. Thank you for your time. Remember again, if this was kind of a teaser to some of the information in VRV Life Systems, if you're looking at getting more information on some of the different aspects of the system, that design workshop might be a good resource for you.
All right, great. Well, thank you so much for bringing us this presentation, or for everyone who joined us, whether you're here live now or later on the recording. Thank you so much for taking some time to join us today. We look forward to talking to you on another webinar soon. Have a great rest of your day, everybody. Bye-bye.